Welcome to our lesson on logic gates. So let's begin with a simple question. Do the streetlights turn on at the same time every day? Is there someone who turns on the streetlights? The answer is no. There isn't somebody who turns on the streetlights. They do not turn on at the same time every day. They work based on the not logic gates. So what is a logic gate? It's an elementary building block of a digital circuit. Most logic gates have two inputs and one output. Both the inputs and the outputs are represented in binary because electricity is binary. Either current is flowing or it is not flowing. So when current is not flowing, we call that a low state, which is represented by a 0. And when the current is flowing, it is what we call a high state, represented by a 1. So let's start off with our first type of logic gate, the AND logic gate. We are now going to look at the circuit equivalent and its truth table. The circuit equivalent here has two switches connected in series with each other. Our truth table tells us under what conditions of the switches being on or off that the filament lamp will be lit. So girls, in this lesson, we're going to get lit. Alright, so let's say we look at the possible option where both switches are off. They're in the open position. If both of these are in the open position, then our circuit is incomplete, so no current will flow. Our lamp will be off, so that's represented by a 0. If we were to leave open switch A but close switch B, it still isn't a complete loop. Hence, our filament lamp will not be on as well. If we reverse that combination, let's say we close switch A, but we leave open switch B. Again, it's still not a complete circuit, hence the filament lamp will be off, 0. Only if we complete the circuit by closing both switches will the filament lamp be open, hence you will have a high output, or in other words, the filament lamp will be lit. So the output is high only when all inputs are high. Let's go to our second logic gate, the OR logic gate. Here, our two switches are connected in parallel with each other. So let's look at the four possible options. Let's say both of them are off. If both of them are off, then no current will flow because the circuit is completely broken. But let's say we leave off switch A, but we turn on switch B. Well, in that case, because they are connected in parallel, then current can flow through switch B, so the filament lamp will turn on, it is lit. When we have the opposite combination, switch B is open but switch A is closed, then it's the same outcome. Current can flow through switch A, so the lamp will turn on. And finally, if both of them are on, then of course current can flow and the filament lamp will be on. So here it is important to note that the output is high when any of the inputs are high. Next, we come to the NOT logic gate, known as the inverter. This is a special logic gate. It is the only logic gate that has only one input. All other logic gates have two or more inputs. So let's look at its circuit equivalent. Here we have a switch that is connected in parallel to the filament lamp. When the switch is open, then the current just flows through the filament lamp. However, when the switch is closed, then the filament lamp turns off. Why is that? It's because the filament lamp has a lot of resistance, but the switch has very little resistance. So when the current reaches this junction and it meets this great amount of resistance, but this very little amount of resistance, if it can flow through here where there is very little resistance, it will flow through that. Remember, according to Ohm's law, current and resistance are inversely proportional. So if there is very little resistance in the switch, then all of the current will flow through that, and very little to no current will flow through the filament lamp. So our truth table is like this. When there's an input of 0, the output is 1, and when the input is 1, the output is 0. So we say that the output is high when the input is low. Now our NAND logic gates. And the word NAND comes from the combination of not and. So NAND is literally not plus and. So we have a combination of a NOT gate and an AND gate. So here we have our circuit equivalent. If both of these are open, then current will flow through the filament lamp. If A is open but B is closed, it's still not a complete pathway here, so the current will flow through the filament lamp. If it's the opposite combination, A is closed but B is open, still not complete, the current will flow through the filament lamp. Only if both of these are closed, then will the current flow through here and not through the filament lamp. This is what we call short circuiting, by the way. There's a shorter pathway with less resistance for the current to flow, hence the term short circuit. So as you can see here, the output is high when any of the inputs are low. And finally, our NOR logic gate. This is a combination of the NOT and the OR. So as we can see here, when both switches are open, then the current will not flow through there and it will only instead flow through the filament lamp. So in that case, the output will be a 1. But if we close switch B, the current can flow through there. It will bypass the filament lamp and then the filament lamp will be off. Same thing goes for the opposite combination. If A is closed and B is open. And the final combination if both switches are closed. So we say for the NOR gate, the output is high when all inputs are low. So here are our logic gate circuit symbols. The AND is like a rectangle with 2 corners smoothed out. The NOT is a triangle with a little circle at the end. The NAND, being a combination of the NOT and the AND, looks like the AND with the circle at the end. The OR is sort of this fish fin kind of symbol. The NOR is a combination of NOT and OR, so it has this circle at the end. And here I'll just mention these other two. There's the exclusive OR and the exclusive NOR. You'll learn more about those at the higher level in 6th form if you continue in physics.